Hello there, and welcome to our AP Chemistry review for topic 3.2, Properties of Solids. In this video, we'll be talking about, like the title says, properties of different types of solids. So there are four different types of solids we're going to talk about. Ionic solids, in which ions are held together by ionic bonds. Covalent network solids, where all the atoms are held together by covalent bonds. Molecular solids, where you have individual molecules that are weakly held together by intermolecular forces, and metallic solids, which have atoms that are held together by a sea of delocalized electrons. So let's dive into each type of these. First of all, ionic solids. Ionic solids consist of cations, which are typically metal ions, and anions, which are typically nonmetal ions or polyatomic ions, that form a crystal lattice of alternating charge. In the example I have pictured here, this is sodium chloride, where you have sodium ions represented by the red dots and chloride ions represented by the green dots. And every single one of these ions is attracted to each other through electrostatic attraction. The positive sodium ions are attracted to the negative chloride ions. Because of these strong ionic bonds between all of the ions in the solid, these solids tend to have low vapor pressures, meaning that the ions don't break apart and create a gas. A vapor pressure is simply a gas above a substance, or the pressure of a gas above a substance due to evaporation or sublimation. High melting points. It's very difficult to melt ionic solids because all of the ions are attracted to each other with strong ionic bonds, so it takes a lot of energy to break them apart. And high boiling points for the same reason. The ions are very strongly attracted to each other. Ionic solids also tend to be brittle. If you apply a stress to an ionic solid, the ions will shift. And when those ions shift, they come closer to ions that have the same charge. If you look at this little example that I have here, this animation, when we apply a stress, the positive ions get closer to neighboring positive ions, and the negative ions get closer to neighboring negative ions, and they repel each other. And that repulsion breaks the ionic crystal apart, causing it to shatter and be brittle, like you're familiar with if you shatter a rock. Ionic solids do not conduct electricity as solids because the ions are locked in place in their crystal lattice. They will only conduct electricity when you melt them and the ions are free to move, because electricity is the movement of charge. So if the charges are not free to move, then you cannot conduct electricity. As a liquid, the ions are free to move, and so they can conduct electricity. Ionic compounds can also conduct electricity when they're dissolved in water. When dissolved in water, as in this animation in the bottom right, the water molecules, the poles of the water molecules attract oppositely charged ions, which pulls the ions apart from one another, and then those ions are free to move throughout the solution, which allow them to conduct electricity because the charged particles are free to move. Three examples of ionic compounds: pyrite, which is iron sulfide, copper 2 sulfate, this blue substance you see here, and table salt, sodium chloride. Covalent network solids are kind of like ionic solids in that every single atom is bonded to its neighboring atoms, but instead of ionic bonds, there are covalent bonds between every atom. And you can have a three-dimensional network of covalently bonded atoms, like in diamond, and also silicon dioxide, which is quartz and sand. Or you can have a two-dimensional network of covalent bonds, like in graphite. And if you look at this animation over here on the right, you'll notice in graphite, you have covalent bonds, which make little hexagons, but those covalent bonds make flat sheets. And those flat sheets are then weakly attracted to each other through intermolecular forces. But the sheets each are covalent networks, and so it is a covalent network solid. Because of the covalent bonds between all of the atoms, covalent solids have high melting points. Three-dimensional network solids also have rigid and are also rigid and hard. Because the atoms are all connected to each other through covalent bonds, it's very difficult to break them apart. Graphite, however, is very soft, just because it is made of those two-dimensional sheets that can slide past each other very easily. These are the most common two substances you need to be familiar with when it comes to covalent network solids, but there are a couple more. um, diamond and graphite, like we just mentioned, but silicon dioxide, which is quartz and sand. Glass is also made out of silicon dioxide, and silicon carbide, where silicon and carbon bond to each other, much like the carbon atoms in diamond. So, three examples of covalent network solids: graphite, quartz, and diamond. And again, for covalent network, you just have to memorize some examples of covalent network solids. Molecular solids. Molecular solids are composed of individually attracted molecules. And the molecules are made out of two nonmetals that are covalently bonded to each other, or two or more nonmetals that are covalently bonded to each other. But then the molecules can be weakly attracted to each other through intermolecular forces. So if you look at this example of ice, you see water molecules, H2O, but then the water molecules are attracted to each other through weak intermolecular hydrogen bonds. And remember, a hydrogen bond is not really a bond, it's an attraction between molecules. And so that attraction is fairly weak, and the water molecules can break apart fairly easily. But each molecule stays intact because the hydrogens and oxygens are covalently bonded to each other. Dry ice is another good example. Dry ice is carbon dioxide. Carbon dioxide molecules are weakly attracted to each other through intermolecular forces, specifically London dispersion forces, because carbon dioxide is nonpolar. Molecular solids typically have low melting points because it's easy to break the intermolecular forces, so it doesn't take a lot of energy to break those intermolecular forces apart between the molecules, and then the molecules are free to move once those intermolecular forces are broken apart. They also have low boiling points. They have higher vapor pressures than ionic solids because they do evaporate more easily. Molecular solids do not conduct electricity because all the electrons are locked in place in those covalent bonds, so there's no free charges to move around in molecular solids. Molecular solids also are sometimes composed of very, very large molecules, such as polymers or other organic molecules that are very large. And those molecules can attract each other through intermolecular forces, and they also can tangle up into one another, creating stronger forces of attraction than just the intermolecular attractions. Three examples of molecular compounds: sucrose, which is just normal sugar that we eat; plastic, which is a long hydrocarbon chains; and ice, which is just water. The last type of solid we're going to talk about are metallic solids. Metallic solids are composed of atoms of metals which are attracted to each other through delocalized valence electrons. And what this means is the valence electrons on each of the metal atoms is free to move to the valence shells of every other metal atom. And so those electrons floating between all of the valence shells, between all of the metal atoms, is the metallic bond between all of the atoms. This is called a sea of electrons. Because of this, metals are really good conductors of electricity and heat because these electrons are free to move. And remember, we said electricity is the movement of charge. So if the electrons, which are charged, can freely move, then they can conduct electricity. Metallic solids also are typically malleable and ductile. And the reason for this is because the metallic atoms are free to move and still be attracted to neighboring atoms because of these shared electrons. So if you apply a force to a metal, the metal atoms will simply shift their position but still share their electrons with their neighboring atoms. And that allows them to be malleable or ductile. Another thing, interstitial alloys. So one thing that metals can do is you can have mixtures of metals or even mixture of a metal with a nonmetal, which are then called alloys. And you can have what's called a substitutional alloy, where in the metal you replace atoms of one metal with atoms that have a similar size. So they're actually substituting into the crystal lattice with atoms that are the same size. That's called a substitutional alloy. Or you have what's called an interstitial alloy. And interstitial alloys have atoms that are much smaller than the metallic atom, and those fit in between the atoms. Usually, interstitial atoms can make the lattice a lot more rigid and decrease their malleability and ductility. So you have a lot harder metals with interstitial alloys. There's still a sea of electrons, so you still have the properties of conducting electricity and heat, but now they're more rigid with those interstitial alloys in there. Steel is a good example of an interstitial alloy where carbon is mixed into the iron. The carbon atoms are much smaller than the iron atoms, and so they fit in between the carbon atoms and make it more rigid. Titanium's a good example of just a metal, and gold's another good example of a metal. So those are the types of solids that will be discussed on the AP test. I wish you the best of luck as you study, and if you have any questions, let me know.